Hello everyone, my name is Matthew Reinhard. I work with Zach Slepian and I'm a PhD student at the University of Florida. And today I'm going to be talking about computing the trispectrum for Axion inflation. And I've included an image here of the DESI focal plane embedded on the night sky. DESI is the dark energy spectroscopic instrument. It's currently measuring the spectra of over 30 million different galaxies and building the largest map of the 3D distribution of matter to date. And we plan to use the DESI data to test the predictions of Axion inflation. So a quick outline of my talk today. So first we'll cover the evidence for parity violation in a large-scale structure. Then we'll talk about the motivation for axions. We'll introduce axion inflation, talk about how to count the different contractions in the trispectrum, followed by techniques for actually computing the trispectrum, and then we will conclude. So I'll start by defining a parity transformation. So parity is an inversion of all spatial coordinates. So here we have a parity transformation acting on a coordinate vector x, y, z, and it causes each of these individual coordinates to pick up a minus sign. And an example of a parity transformation that we're all familiar with from our daily lives would be looking at ourselves in a mirror. So here we have a right-handed coordinate system, and its mirror image has the z-axis inverted, making the mirror image a left-handed coordinate system. So this is why when you look at your right hand in the mirror, it appears as a left hand. So we know that the universe is highly homogeneous and isotropic, but what about handedness? Are there more right-handed or left-handed configurations of galaxies, or are there equal amounts of both? So we can actually define the handedness of a quartet of galaxies, a group of 4 galaxies, in the following way. Let's consider one galaxy, we'll call that our primary, and that'll be represented by this red dot here in the figure. And then we pick 3 other galaxies and draw vectors R1 and R2 and R3 to the other 3 galaxies, such that R1 is the vector to the closest one, R2 is the vector to the next closest, and R3 is the vector to the furthest. Now, if we trace around this tetrahedron, which is formed by these 4 galaxies, if we move from R1 to R2 to R3, we see that we move in a clockwise fashion. But now if we consider the mirror image of this tetrahedron on the right, and we trace around from R1 to R2 to R3, we will move in a counterclockwise fashion. So we've actually defined a handedness for these tetrahedra, which really represent 4 galaxies. In 2022, a paper published by Jiamin Ho, Zach Slepian, and Robert Kahn reported evidence of parity violation in the large-scale structure at 7.1 sigma. And a paper published in the same year by Oliver Philcox also detected parity violation at a lower statistical significance. And the way these papers detected parity violation was by measuring the 4-point correlation function, or 4PCF. The 4PCF is the simplest statistic sensitive to parity violation, and it's measured by taking the ensemble average of these density fluctuation fields, delta, at different spatial locations. And what this amounts to is essentially adding up all possible combinations of these tetrahedra and counting the number of right-handed and left-handed ones. And these groups actually found an imbalance, which indicated that the large-scale structure may in fact violate parity. So if there is in fact parity violation in the large-scale structure, the natural question is what could have caused this parity violation? So we know that all fundamental interactions are parity symmetric, except for the weak interaction. However, the weak interaction really didn't play any significant role in the formation and evolution of the large-scale structure of matter. So any parity violation in the large-scale structure must have come from some new physics early on in the universe. A parity violating interaction during inflation could potentially seed the parity violation that we observe today. So one particle that may be responsible for the parity violation in the large-scale structure could be the axion. The axion is a hypothetical particle whose existence was conjectured to solve the strong CP problem in particle physics. So the Lagrangian of quantum chromodynamics, or QCD, contains a CP violating term. So C here stands for charge conjugation, which is an operation that takes particles to antiparticles and vice versa, and P stands for a parity transformation. So this term in the QCD Lagrangian here actually is not invariant under CP, but every experiment involving quantum chromodynamics that's ever been done has not observed any CP violation. So experimental bounds require this parameter theta to actually be smaller than 10 to the minus 9. So this is the strong CP problem. Why is theta so small, possibly even 0? And a solution to this problem was introduced by Pesce and Quinn, and their solution involved the introduction of a new global U1 PQ symmetry, and the breaking of this symmetry leads to the production of axions. Now, the vacuum expectation value of the axion exactly cancels this CP violating term in the Lagrangian, solving the strong CP problem. So inflation was a period in the very earliest moments of the universe where space-time expanded rapidly. The standard model of inflation actually preserves parity, so we need to look to an alternative inflationary model that could potentially explain this parity violation that we observe in the large-scale structure. So axions are pseudoscalars, meaning they pick up a minus sign under a parity transformation. So here we consider axion inflation, where the axion is coupled to a U1 gauge field. So here is the inflationary action, and phi represents our axion field, and F mu nu is the field strength tensor defined here, given in terms of derivatives of the gauge field A mu. And this is a general gauge field not necessarily associated with the electromagnetic force potential. So the important term in this action that we should focus on is this last term here, because it represents a interaction between the axion phi and the gauge field A. And this is a parity violating interaction, which could source our parity violation at late times. We work in the Coulomb gauge where the temporal component of A vanishes, and the spatial components can be written in this decomposition of circular polarization vectors epsilon. And these are the annihilation operators of the gauge field quanta, and capital A sub lambda are the mode functions for the gauge field. So we want to relate this parity violating interaction during inflation to the parity violation that we observed in the large scale structure. And the way to do that is by computing the 4-point correlation function, or its Fourier space analog, the trispectrum, of the primordial curvature perturbations, zeta, which can be written in terms of perturbations in the inflaton field phi. So the axion is our inflaton field in this inflationary model, and it can be written, the axion field can be written as a background value which is constant in space but varies in time, plus some small perturbation on top of that background value. And these small perturbations in the axion field can be written in terms of a vacuum contribution due to vacuum fluctuations, plus a contribution due to the inverse decay of gauge quanta into inflaton perturbations. So here we write down the trispectrum of these primordial curvature perturbations. It can be written in terms of Q-vac, which are just the Fourier modes of these vacuum perturbations in the inflaton field, and Q-inverse, which are the Fourier modes of the inverse decay perturbations in our Axion field. And these inverse decay perturbations are really the source of our parity violation, as they are produced by the interaction between the axion and the gauge field. So these inverse decay Fourier modes can actually be written as the integral of a Green's function against this source function J. So the source function is the non-homogeneous term of the equations of motion of our inflaton perturbations. So J is written down here in terms of the creation and annihilation operators A and A dagger of the gauge field. And we see that we also have the gauge field mode functions in this expression. So the parity violating piece of our 4-point function of our trispectrum can be written in this way as the essentially the trispectrum of these source terms integrated against these 4 Green's functions. Now to compute this correlation function of these source terms, we have to take lots of contractions of these creation and annihilation operators. And there's a nice diagrammatic way of counting up all these contractions that we show here. So these red squiggly lines represent the internal lines correspond to the gauge field. And if we look at Q1, there are 6 different places with which we can contract to form a one-loop diagram. And once we make a choice, there are now 4 different places to contract the Q1 minus K1 leg. And once we make that choice, if we look at the Q2 minus K2, there are 2 places to contract. So 6 times 4 times 2 gives 48 different terms. So the correlation function of those 4 source terms will involve 48 different terms that we will have to integrate. And one such term is given here. And all of the other terms are identical to this one, except that the arguments in the delta functions may be rearranged. So if we were to integrate out all the delta functions in this expression, which we might be tempted to do, we would still be left with a 12-dimensional integral. So instead of doing that, we'll actually reduce the dimensionality of this expression by expanding the delta functions. So we expand the delta functions by first writing them in terms of this integral over a complex exponential. And then we insert the plane wave expansion here for the complex exponential. And once we do that, with some work, we can recognize that the integrals are actually convolutions, and then use the convolution theorem to turn this into a problem of taking a sequence of Fourier transforms and get rid of this k minus q shift. So when we insert the plane wave expansion for these delta functions, we get this expression here. And although we've picked up some new integrals over these dummy variables x1 to x4, we've also been able to decouple all the 4 momentum integrals. And they all take on essentially the exact same form. So if we can compute a general integral of this form, like one of these momentum integrals, then we'll have gone a long way in simplifying the trispectrum computation. So here we consider one of these general integrals. And the next thing we do is plug in this dot product of these circular polarization vectors. So there are 7 different terms, and we were actually able to recognize that each of these terms turn into a convolution when we plug this expression in. And then we use the convolution theorem to start taking Fourier transforms. And we were actually able to do all of the angular integrals associated with these Fourier transforms, and we were left with these radial integrals given here at the top. And from here, we did some changes of variables given here, and we also brought in that time integration. We brought in the Green's function and integrated against time as well, and ended up with this expression here. So in conclusion, we've shown how to simplify the calculation of the trispectrum for Axion gauge field inflation. We will use these techniques to numerically compute the trispectrum and explore the parameter space of wave numbers. And ultimately, we will use the DESI data to make a robust measurement of the galaxy 4-point correlation function and search for signatures of this Axion gauge field inflationary model and constrain the physics of the early universe. Thank you.